All right, so given this function here, f of x equals x squared minus 1, we introduce our notation right away for function notation, f of x. And when we see something like this, notice there's this x idea that goes with the function, and what that x idea is basically saying is, hey, this value right here, whatever it is for x, I want to plug it into this function and how it's defined. So since this value right here represents the x, kind of like on this first example here, my x would be 3, I want to take that value, I want to replace all the x's that I see over here in the function. So sometimes, because of the order of operations and potential sign mistakes, it's kind of nice when you have these functions defined to go ahead and maybe slap some parentheses around the x's that you see in the function, and then understand on a problem like this first one, if I'm taking 3, I'm plugging in for that x, well, I'm just replacing everything that's inside the parentheses and going from there with my order of operations. So I plug 3 in, I square 3, get 9, I subtract 1. I find that the value of this function when x is 3, because that's what this means, is equal to 8. So if that makes any kind of sense. For the next one, we substitute 5 in the place of x. So I've got my x up here that is being squared. I'm going to substitute 5 in its place, subtract 1. I calculate that out. 25 minus 1, we get 24 back. So for this function, when x is 5, the value of the function, as we would say, is 24. Having these little grouping symbols that we put in here, like the parentheses around the x, do come in handy, like I said, because of potential sign mistakes. So when we get to something like a -1, we insert that in, just replacing the x inside the parentheses, which again is being squared on this one, then -1. -1 goes in, we square that negative, we get +1, subtract 1. The value of the function would be 0 when x is -1. Okay, plug in 0. The nice thing about plugging in 0 is any of the x's you see in the function, you know, if we got all these terms floating around that have x's in them, they're just going to drop out, right? Because they're going to become nothing. So essentially whatever's left over here, like on this one, you'd have 0 squared minus 1. That -1 is all that's left over, so -1 would be the value of the function when x is 0. And then just to conclude this idea, take -2. You're trying to find f of -2. -2 goes in, square that, subtract 1. -2 squared would be 4, -1, get 3. So all these answers we came up with, these are values for the function at each of their respective x values. All right, so new example, g of x is defined as the square root of 5 minus x. Basically, I'm going to work my way down here. Got these x values. I'm going to insert into my function for g. I'm going to replace all the x values that I see within that function. In this case, just one x value to replace, kind of like the first example. So when I plug in 4 to find g of 4, I get the square root of 5 minus 4. I'm going to leave the parentheses in, leave the parentheses in. But basically, you got the square root of 1, right? Square root of 1 is 1. So g of 4, when we evaluate that, is equal to 1. You take 3, you plug in. You got the square root of 5 minus 3. 5 minus 3, of course, is 2. So you're taking the square root of 2, and the question would be, how do I express that answer? Well, just leave it as the square root of 2. That's exact. It's an irrational answer. That's okay. If you had to graph it out and plot that point, then yeah, take the square root of 2, get that decimal, plot it out. But since we're just evaluating here, we like to leave answers as precise as possible, leave it as that square root. Same kind of thing is going to happen here when you find g is 0, right? If I plug 0 in, I get the square root of 5 minus 0, meaning I have the square root of 5. Can't do much better than that in terms of exactness. For g of negative 2, square root of 5 minus, maybe parentheses helps here in the substitution, because you're subtracting a negative, right? But we know what happens with that double negative. We know how that creates the positive situation, so you have the square root of 5 plus 2, which would be the square root of 7. A lot of irrational answers here. And then we get down to g of 7. All right, when we consider g of 7, that's the square root of 5 minus 7, which would be the square root of negative 2, right? Square root of negative 2 is imaginary, meaning the actual value for this would not be real. So g of 7 does not exist. First function that's defined, f of x equals 2x plus 1. Second function, g of x equals x squared. Just as we saw in the previous examples, if it helps, for each function that's defined, wherever you see an x, maybe throw some parentheses around those x's to say, eventually I want to substitute some values in those places. But as it's defined for these two functions, you want to determine the value of the following. Starting with f of g of 3. If I rewrite that using the definition that I now know for composite functions, I could write it as f of g of 3. That might make a little more sense to me based on what we did before, because if I work from the inside out, I start by figuring out what g of 3 is. Now, what g of 3 is, I got to use the function g to figure out g of 3. So I take this 3, I insert in for the x for that function. That would be 3 squared, right? I get 9. This becomes 9. So now my goal is to figure out f of 9. If I want to figure out f of 9, now I got to go over here to the other function f. 9 is the value that replaces the x's I see within that function. So if I need to write it out, it'd be 2 times the x, which would be 9 plus 1, right? That'd be 18 plus 1, so 19. We've now plugged into both functions, which is what this wanted us to do in the first place. And the value we got back when we combined these functions was 19. That's our answer. All right, number 2. You're trying to find g of f of 3. Careful. You're going to find g of f of 3. You're going to start inside the parentheses, work from the inside out, find f of 3. To find f of 3, you are taking 3, you are plugging into the function f. So function f up here, I'm plugging 3 in. It'd be 2 times 3, 6 plus 1, 7. So now I know what that inside part is, f of 3. That's 7. I'm going to take that value and plug into the function g. Again, working my way from the inside out. So plugging in the function g. This value of x, which is 7, goes into that function. That 7 for that function would be squared. So my answer is 49. All right, so for the third one, we're going to find f of g of negative 1. Working from the inside out, g of negative 1. go back to the function g. -1 goes in the place of x. -1 would be squared, so I get +1 back. That means my new problem to figure out at this point would be f of just 1. And if that's the new problem to figure out, trying to find f of 1, I now play with the function f exclusively. I plug 1 in the place of x. I get 2 times 1, 2, plus 1. F of 1 would be 3. Okay, if we're good with this so far, let's skip down here to one where we're combining into the same function twice. Maybe that'll be more interesting. I don't know. If I go down to, say, f of 3. You play with f of 3, working from the inside out. Inside out, you start with f of 3. Go to the function f, replace the x value with 3. So it would be 2 times 3 plus 1, we get 7 back. So the new problem becomes f of 7. Okay, take 7 now. Plug that into the function for f. We're still working with that same function. So back here, plug in for x. It's 2 times 7, so 14 plus 1, that'd be 15. F of 3 equals 15.